Before the midsem, we saw how to make flowcharts. We now know how to make level 1 flowcharts and level 2 flowcharts. Today what we are going to see is how to make data path control design from flowcharts. But before that, we just left out a little bit about flowcharts. So we'll finish that and then move on to data path control design. Okay. So what we left out was see, this is the flowchart. Okay, this box which we did last time, in which we specified the various tasks, and then we gave some labels, and also we indicated this, right, wherever there was one external and a bus activity involved, we had put an box out here in the top right corner. Okay, but over and above that, for each of these boxes, we can write some state identifiers also. So once we write the state identifiers, it becomes pretty easy for the hardware engineer to understand what is required from this particular box, and accordingly he can easily implement the hardware. Okay, so there are several state identifiers associated with the hardware flowchart. So let's see what of them. Okay, so the first one on top we are out here is label A. Okay, so the label A, this we already did, where we indicate whether it is an register to register operation or register to memory operation, and also this arrow indicates that the final answer here in this particular case Rx, op and op Ry. It means the operation is to be done between Rx and Ry, and final result is to be stored in Ry. Okay, so that this is to be clearly indicated out here. Similarly, if I give one more example here, Rx op. Now, op is generally an add or whatever is the operation which we need to do. Okay, Rx operation memory, and the final result is to be stored in memory. Okay, so that is clearly written here. So what are the two things on which the operation needs to be done, and where the final result needs to be stored. Okay, so that is indicated here in the label A. Okay. And in the label B out here, we indicate what is the actual operation to be done, whether it is an AND operation, what the ALU is supposed to do. So that is mentioned in the label B here, AND, subtract, or okay, all those kind of operations, exclusive or shift operation, whatever we want the ALU to do. So that is written in label B. Okay. This, okay, like we said, whenever there is an external bus activity involved, we put this out here. Okay, there are other labels. Now let's discuss each one of them. Okay, now here we mentioned the access type. Okay, so we write dr whenever we are reading a data from the memory. Okay, so for all those operations where data is being read from the data bus, from the external data bus, when we are going to read some data, we write a data read. Okay. Similarly, if you have to write some operation from the ALU or from one of the registers of within the execution unit to the memory, in that case we have a data write operation. Okay, see, this data write doesn't mean data within the execution unit from one register to other. Okay, it is only when external memory. Okay, so this is with respect to the external memory that we need to remember. Okay. Similarly, when an instruction, if we are going to read an instruction, okay, from the memory, okay, we don't write an instruction. Obviously, we don't write. Programming is different. So once a program is written, once one instruction is executed, we read the next instruction. Okay, so whenever we do such an instruction read operation, we indicate here as IR. Okay, and we write NA whenever we are doing an operation within the ALU, we are not accessing the memory at all. So in those cases we write as NA. So this is what an access type is indicated out here. Okay, so there will be a two-letter word written there, DR, DW, IR or NA. Okay, that will be written there. Similarly, here we write the actual operation which is expected out of the ALU. When you have a flow chart which will have 2 or 3 steps, on top we write generally add, subtract and all. Okay, but within that, if in one of the blocks, if some activity is to be done which is different from the overall operation out here, right? Suppose you are doing some register to register subtraction operation, but within one of the tasks will be to increment the PC, right? So that particular small box, okay, within the big flow chart, okay, there it is supposed to do only add. Okay, so you have an operation out here, ALU operation. You can specify that also here. Okay, this is again and or we can specify within this box. So when we take some examples, it will be very clear. Okay, and this is the flags. Okay, condition code setting. Okay, we write S means condition, the like the flags, whatever is the flags. Okay, they have to be updated based on the arithmetic logic operation which is being done. In certain application, in certain operations, we are not interested in what is happening to the flag. For example, if you are increasing the program counter, okay, in those cases we are not interested in what is happening to the flag, right? So we need not, but whereas we are doing some addition, subtraction, and those kind of operations, okay, suppose we are decrementing a counter, we want to see whether the counter has reached to 0 or not. So in those kind of things, we have to check the condition of the flags, right? So that is all. Similarly, when we are doing a multiplication or division, those kind of operations, we check what is the condition of whether an overflow has occurred or not. And after addition, if it whether the result is beyond the computing capability of the ALU. Okay, so all those, whether the overflow flag, so we need to verify the overflow flag. So all those things. So whenever we do an the ALU operations, okay, where we need to check the conditions of the flag, we write S. If it is if we don't have to check, generally for PC increment and decrement, so we write N, and X stands for don't care. So here we write either S, N, or X. Okay, duplicates. Okay, here this is not used in the min instruction. Generally, if you have an similar thing in some other flowchart also, then you can use the duplicate. So that is not used. Page and location is also not used. Okay, and then coming to next state. Okay, next state is it is like if it is after this, if we are going to have an branching operation, then we write an BC. Okay, branch conditionally. After this particular task, if we are going to go to the next instruction, we are going to write instruction branch. If we are going to if it is within the part of an instruction, then we write a sequence branch. And then if you are going to jump to an like unconditional jumps you have, right, where after executing this in that particular task, there might be an unconditional jump where you might have written, okay, now the program has to jump to a specific location. In that case, we write direct transfer. Okay, these things will be clear as we take a few more examples. Now access with and synonym, these things are not used. This is the state ID. Okay, so for each of these things we have to give some name, so that that becomes the identification label of this entire block. Okay, so we see some examples, then things will be clear out here. Okay, so the first example out here is add Rx and Ry. Okay, so if you see here what is done in the first box out here, you have Rx being through the A bus, internal A bus is being brought to. So this is register to register operation, right? So add Rx and Ry. So we are doing register to register operation. Hence we write register to register, and then it's an add operation. So I write an add out here. Right, now Rx I am going to get into ALU, Ry I am going to get into ALU, right. So here it is external data bus is not used, access type. So I write NA here. Okay, here I write op, because this is add which is written here, that needs to be done here. So that is why operation I write. S means the flag. Okay, the flag after this the conditional flag needs to be set. I write S out here. Okay. This is the identification operation, register to register 1. Okay, so I have given this. You can give any your own nomenclature, but I have given it because by reading it, it is very clear. It is operation register to register. Okay, 1. And after this is next what it is. It has to go to this state. Operation register to register 2. So here I am writing operation to operation register. This is the next state. So this is the next state. So each one of them will get coded in the control unit later on. Okay, so that is why. So it will pick up after implementing this. It will go to this. It will from the control in the control store. It will pick up this particular block. So what is this block out here? Now if you see here, now after having done this, the result is available in T1. Okay, after adding. So T1 from the T1 through the B bus, it is being brought to RY. Okay. Also we need to increase increment the count of the program counter, right? So if you see here, this is the program counter. So that is being brought to ALU, and similarly it is also brought to the address output bus bar. Okay, that will enable fetching the next instruction bus. So from the data bus, the next instruction is being fetched to the instruction fetch register. Okay. Also you are incrementing the count of the PC out here. Okay. This PC was increased in the previous step itself. So this is not this. The present count in the PC is not indicating this. It is the next one. Okay. So the next is being the next instruction is being fetched out here. Parallelly, you are increasing the count of the PC also. So for that you are bringing you are putting +1 into the ALU also, right? Now here, since you are specifying what the ALU is supposed to do, you are writing an AND out here, right? So and then now since I am only increasing the count of the PC out here, so I am not interested in the flag out here, right? Because I am not doing an actual addition or subtraction with respect to data. I am just increasing here, adding 1 to the program counter. So I am not interested in the flag. So I write in a dash n out here. Okay. So if you see here, so these are the labels which come here, right? Now operation 2, and then operation from operation register to register 2. This is the label which I have given here. This is going to be the next label here. Operation register to register 3 out here. So in this again, whatever was being fetched from the next instruction, what was fetched, that is being transferred to the instruction register execution block. Okay, and here if you see here, ALU is not used, so I have put an X out here, right? And hence there is no flag requirement also. There is no data being fetched from the external bus, so this becomes NU. And in the T1 we have this, right? And we have done +1 to the PC. So the new updated value of PC. Now from T1 we are bringing it to PC. Okay. So now is it clear how to put these labels? All of you? Is it okay? So let me give you one more example. If you have doubt, please ask me. So once you are, you should be very clear how to make a flowchart and write the labels. Okay, this is important from your exam point of view also. So if you have any doubts, please stop me. Okay. So let's take one more example where I am loading the data from RY to RX. Okay, so I am loading a data. So here we are starting as here, right? R by RY. Okay, through data bus B, it is being brought to RX. Okay. Simultaneously, we are putting the data into T2 also. Okay, I'll tell you why it is being put into T2 in the next step. So we are putting it into the T2 also, right? And also in the program from the program counter. Okay, we are assuming that in the previous instruction the program counter was updated. So now while doing this instruction, we saw this earlier also when we did the flowchart. We always have to any instruction. The responsibility is not only to do the particular arithmetic logic operation, but also to fetch the next instruction is also part of our task. Okay. So now here, whatever was the PC which was incremented during the last instruction, that is being put to ALU and also to the address output buffer. So once you put that PC address into the address output buffer, so data will be available here. So that will be put into the instruction fetch register. And since it's a data operation, okay, I put a external bus is activated. I put a box out here, and then I read IR. IR means an instruction fetch, right? When we saw here. here an access type. Okay, so they were IR means instruction read. So that is what. So instruction read. I am reading an instruction. So that is the reason I have put IR. Here, if you see RB, I am getting it to RX. So I am I have to add. Okay, the here I am doing an add operation. Okay, because this is just a load operation, right? But here within the ALU, I am supposed to add +1 to the ALU, right? So that is why I am writing add here. So now see, these two are different out here, right? So this is a load operation, but then here in this block I am putting the value of PC to ALU, and I am also writing +1. So they need to be added. So that's why I am writing add. And since it is just a program counter increase, so I am not interested in the flag. So I write out X out here. Okay. Okay. Coming out here for the next instruction. So once that is done here, in the next, whatever was fetched in the instruction fetch register, that is being transferred to IRE. So now the external here, it is not an data transfer or an instruction, so transfer, so that this becomes NA. Okay. Now what we are doing is from T2 we are getting it to. So I told there is a reason why we are while we are doing transfer from RY to RX, we are also putting the data into T2. Now why we are putting that T2 will be clear out here. So T2 is also brought to ALU, and we are putting a 0 also into ALU, and doing an add operation. Okay. So what happens is if the content, so the flags get affected. So suppose that data what was transferred from RX to RY, if it were a positive number, okay, since we are adding 0, nothing would change. Okay, but the flag will get updated with the 0 depending on the data. So whether it is a negative number which was transferred, positive number, or a 0. Okay. So all those things get affected here, but the data doesn't get changed, right? Whatever data from RX has got transferred to RY. Parallelly, we have transferred it to T2 out here, and then T2 we are getting it to ALU, and we are also putting a 0 into ALU and doing an add operation, and we are enabling the flag. That is just to check the state of the data which was transferred, whether it was a 0 data or a positive data or a negative data. Okay, so that is the reason this has been inserted out here. Now this is the label. Labels we can, like I said, we can give any label of our choice. But here what I have given is load register to register 1. This is the label for this particular block. Then it goes to load register to register 2. Okay. Here register to register, this is the label here, load register to register, and then this is the end of the register of the flowchart for this particular instruction. So I go to IB, that means the instruction branch. I go to the next instruction now, right? If you see here in the previous case also, here from Op1 to Op2, then Op2 to Op3, and then Op2 to the IB. IB is the next instruction. Okay, I am going to the next instruction branch. Okay, so that is what, this is how we give the labels. So store is just same as this, only thing is that this is swapped. So you can have a look at once I share the PDF out here. So I can also have an execution sequence with memory operation reference. Okay, let's see how the labels are put here. So I have a memory to register operation load. That means the data of the memory is to be brought, data available in some memory which has been defined is to be brought to register RX. Okay. Now again here we are assuming that that memory address, okay, was placed into the AO register from the PC in the previous operation itself, right? So in the previous operation, PC, okay, we are going to put it into so that data whatever was available in the memory, okay, that was decoded in the previous instruction. So the data is already available here in the DI register. Through B we are going to getting it into RX, again to check what is the kind of data which is there, whether it is a positive number, negative number. To check the status, we are also getting it into T2. Okay. So we are not now, if you see here, every instruction we said some instructions will be prefetched and done. Some task will be done by the previous cycle. So here also we are assuming that the contents of the memory was already fetched and available at in the DI register out here. So that is why it started from here. Okay. And now we are supposed, in this particular instruction, we are supposed to increase the program counter value, right, and get the next instruction also. So the whatever is the PC, we are going to put it into the AO. So we are going to get the next instruction. So the next instruction which is available in ED external data bus is going to come into IRF. So it is an instruction fetch register action. So I write IR and I write AD, because again parallelly the count of the PC is being increased. So I have put +1 all to the also to the ALU. Now I have to tell the ALU what is to be done, right? So I have to do an add operation, and since it's an PC incrementing thing, so I put X out here because this is not important out here. The flag is not important out here, right? So load register memory 1. This is the label. Load register memory 2. This is the next. So load next, it has come here. From here, what we have done, we have already brought the data to the instruction fetch register. From there, we are moving it to the execution register out here. From T1, T1 has got what? PC +1 now here, right? So we learned that every time an ALU does an operation, the output of the ALU will be available in T1 register. So from T1, okay, through B, now it is being brought to the program counter. So the program counter is being updated out here, right, with the new value. And T2, what is T2? T2 was the data which was available here, right? The data was stored also in T2. So we are doing an T2, we are getting it to ALU, and we are also putting one 0 into ALU and doing an add operation just to check what kind of data it is. Okay, so we are enabling the sign flag out here. So this is how we do, right? Okay. Now this is again end of the instruction. After, so I go to instruction branch. So this is the label which it comes out here, right? So this is the one. I think another few more examples are there. Okay, this is I think we did this. Okay, this is register to memory. Okay, now a content from register to memory is being moved out here. So you have RX through A, it is to ALU, also to the data out here, right? Data out register. So you see here what is written here, a data write operation. It's a data write operation, right? So let me just cover these labels out here. This flowchart, since we have done it last time, so only addition what we have done it, we have put some labels out here. So we'll focus on this labels aspect here. Okay. So similarly, here we are from T2 we are getting it to and we are getting 0 also to the ALU to check the status of the data, whether it is an 0 data or a plus data or a negative data or some overflow occurred. So to check that aspect, what we are doing is we are doing an add operation and also enabling the flag out here. Okay. So if you see here, now in this operation similarly, if you have a look out here, right, this is an instruction fetch register, because from a PC, right, you are getting it to the address out bar, and from the address out bar you are from the data bus you are getting it to the instruction fetch register, right? So that is why this label is IR, instruction fetch register, right? Instruction fetch action, and that is why I have written it here the label as an IR. And again PC, you are adding the contents of the PC, you are incrementing the contents of PC, so I am writing +1 out here, right? So this is add dash n. Okay, since it is just an PC increment action, so I don't require the status, so it is add n. So just have a look at these labels out here. Okay, so so now I have IRF. So IRE, and here it is just an there is no external data bus requirement out here, so it becomes an NA, right? Similarly, here we are not expecting the ALU to do anything, so it becomes X dash N. Okay, so what I am going to do is I am going to share this PDF. So there are another 2 or 3 examples written out here, right? So each of them I have given the labels. So try to analyze these labels and why it is written in this manner. So the same logic applies everywhere, right? So the procedure to write labels is given in this particular slide. So you can verify. Okay, so these flowcharts which we already done in the previous classes. Only addition what we are doing right now is we have added labels everywhere out here. Okay, so you have to go through all these things and then verify whether those labels are correct or not. Okay, so let me just explain you 1 or 2 more examples. Okay, here if you see here, now this is an let me start from here. Okay, this is the branching operation, right? So in this branching operation, what we learned, this also again we learned in the previous case, previous class. If a 0, if we are encountering a 0, then the program counter needs to be loaded with the contents of RY. That is known as a conditional jump. Okay, so how to write a flowchart for that? So here we are assuming that we have encountered an 0. Okay, in that case, if you see here, the contents of RY, okay, is through A, it is brought to ALU and to the address out bus bar, and we are also now the adding +1 to the ALU, so that the program counter first of all the contents of RY. So once you place it to the address bus bar, so that program whatever is written in the location specified by RY is being brought to the instruction fetch register, and also you are doing +1 so that the PC can be updated accordingly, right? So this is already we are assuming that okay, the 0 has been encountered, and if the 0 has been encountered, the next action will be from IRF you get it to IRE, that is the whatever you have fetched you are going to get into the execution register, and since you have put +1 out here already to the ALU, now if you see here these labels, okay, this is a branch 00, I have put 1 here, so this is just a label. Now here I am putting BC, that means branch conditional. So see the difference in the label. So you have to focus on the labels out here. It is BC out here. Here I am doing an add operation. I am increasing the count of the PC. So I am not interested in the flag. So I have just written IR add out here -n, and IR because I am fetching the instruction. So I have written IR out here. Now if it is Z is equal to 1. So since I have already fetched the new instruction, I am going to put it into IRE. T1 has got whatever was the value of RY +1 now here. So that is to be loaded into the PC out here. Right. So here again ALU is not involved in this particular here. So X and N, and also external bus is not involved. So I have written NA. And branch 2. Now this branch operation is complete. So now I am not writing BC. Branch operation is complete. I am writing IB. So I am going to the next instruction out here, right? But if the 0 condition is not satisfied out here, then okay, then I have to continue with my program. I don't jump, right? So now where is the count available? It is available in the PC. So that PC is again brought to AO, and from external database again IRF will be updated here. Initially into the IRF we had brought the new instruction corresponding to RY. Now we are going to get the instruction which is pointed out by the program counter. So EDB to the IRF +1 again to increase the count of the PL, and then the next IRF to IRE, and the +1 the incremented value of a PC which is available in T1. Okay, T1 always gives the after the operation of the ALU, whatever is available that is available in T1. So that will be brought into PC out here. Okay, so this is how this is done. Now if you see here, when we make flowcharts for many instructions, some blocks may be common out here, right? So this is common out here. So we can actually, if required, we can name this block also as an OPRM4, okay, and then because this is the same block, so that will, when we make the hardware, so the in the control store, okay, this will not get stored as an separate, because the actions are are exactly the same. So in those case, these identifications of these blocks can remain the same. Okay, so that just keep that in mind. Okay, now let's take one or examples out here and see how the flowcharts along with the labels can be written. Okay, so if you see here, this is one example out here, right? Rx, what is to be done is the instruction examines the number stored in the register Rx and stores back the magnitude of the value in the Rx. That means we have to examine what is there in Rx, whether it is a positive number or it is a negative number. Okay, so if it is a positive number, we leave it as it is, and if it is a negative number, then we have to swap the contents of that register. Now we have to change the sign of the register and pick only the magnitude. Okay, so how to do that? So how to do that is, now see here, from the register Rx through A, we are going to get it into ALU. Okay, so once it is done, you have an NA out here, because we are not referring to any external bus out here, right? No data transfer, it is within the execution unit. So this becomes NA. 0 also we are going to get into ALU, and we are doing subtraction. Okay, what we are doing is we are doing 0 minus Rx. Okay, so always when we do the subtraction, remember that this takes the priority, whether the K. If you remember the value, it is always A bus will be subtracted from either B bus or from the constant. Okay, so it will do 0 minus A. What is 0 minus A? It is actually, it takes a 2's complement value, right? So now and also you are checking the sign. Okay, so now two things can happen. Okay, once you are doing 0 minus A, right? If A were a positive number, okay, if A was a positive number, then when you do 0 minus A, right, you will get a negative number, right? So negative is equal to 1 you will get here. N is equal to 1 means negative is equal to 1. So you are checking the flag also. Suppose A is equal to a negative number, when you do 0 minus A, okay, that means you will get a positive number, right? Because A is negative. So N is equal to 0. And also when we do 0 minus A, right, if it is a negative number, what happens is when we do 0 minus A, then the magnitude changes, and the answer what is available will be positive, because you are doing 2 minus here, there, right? So the minus gets removed. So both things happen. Okay, is this thing clear? Okay, let me repeat what I said. Okay, what we are doing is we are doing 0 minus. We are checking this instruction whether the number stored in register Rx. Okay, and then if it is a positive number, we leave it as it is, and if it is a negative number, then we are going to change the sign, because we are just interested in the magnitude. So we are going to change the sign and keep that number in the register Rx. Okay, so what we are doing is we are getting from the register Rx, we are getting through A register, we are going to get it into ALU, right? And also we are putting a 0 into the ALU. Okay, and then we are doing a subtract operation. We are doing 0 minus A. Remember, it is not A minus 0. We are doing 0 minus A. Okay, now if it is a positive number, okay, the result, okay, because I am writing subtraction and I am giving S. S indicates the sign sign flag needs to be activated. If sign flag is activated, then if it is a negative number, okay, then the condition is different, and if it is a positive number, it is an condition is different. And if A is less than let's see what is being done here, and then we'll go to this branching operation. What is done out here is, now in the T1 register, okay, what is in the T1 register? The result of this operation, right? That is being brought into T2 out here, okay. And from the PC, now I need to increase the program counter value also. So this is a standard thing which we need to do in every operation. So we need to fix where to put this, okay. So I have put it here. Now from the program counter, I am getting it to ALU and to the address out bus bar, and I am putting +1 also to the ALU. Now when I do this here, obviously the data of the T1 will be updated, right? And that is why I am getting this data of the T1 to T2, because T1 will now contain the updated value of the PC at the end of this operation. So that is why I have shifted this data which was available in T1 to T2, and what is available in T1 actually is 0 minus A, right? Now if you see negative is equal to 0, negative equal to 0 means it was a negative number initially. Since I did A minus 0, I got a positive. That means negative is equal to 0 here. So that means I have now whatever is available in the T2, okay, since I have done A minus 0, that has now become positive, that I am going to get it into Rx, okay. And then in T1, I have that updated value of PC, so that I am getting into the PC, and from instruction fetch register I am going to get it into the instruction execution register. Here again external data bus is not required, so I have put an NA here. Here there is no arithmetic logic operations being done, so I have put an X and minus. Okay, and there is no flag also a requirement out here, right? Okay, so this is now, if you see, if it is a negative, that means A was actually positive number, okay. In that case, I just leave the register Rx. Here Rx is being updated. Since Rx was positive earlier, right, the result will be positive out here, right? The result became negative here when I did 0 minus A, because Rx was initially positive. So in that case, I don't do anything. I don't disturb the content of Rx. So I don't do anything here, right? So now simply I am going to just update the program counter and move forward. Okay, so this is now, if you see here the labels. Okay, this is one. Now, okay, ST is just the name label I have given. From ST to ST2 I am going here. From ST2 to the branch. So here I am writing BC. That means I have to do a branching operation out here, right? And here, if you see here, ST3, ST4 I have written here. This is an IB. Okay, IB means this is the end of this particular instruction. So, and that is the reason it is written an IB out here in these two places. Okay, so this is how we do an hardware flow chart. Now let me give one more example out here. I think which is sort Rx and Ry. Okay, that now again at the rate it is written here. That means now whatever is the contents. Okay, this is Rx. We are not checking the contents of Rx and Ry, but the addresses. We are checking the contents of two memory locations. The address of the memory locations are given in Rx and Ry. Okay, so that is the reason at the rate it's written out here. Okay, we are not checking the contents of Rx and Ry. We are only checking the contents of two memory locations whose address is given by Rx and Ry out here. Okay, and then after checking that, the lower value, okay, whichever is lesser value, that needs to be there in Rx. Okay, if the lower value is in Ry, then we need to swap the contents. Okay, we need to swap the contents. So how to make a flow chart for this? Okay, so this is the flow chart out here. Now if you see here, EDB from Rx, okay, the memory Rx, okay, the memory address is given in Rx, that you are getting into AO register. Okay, so now once you get it into the AO register, that the contents of that memory will be placed in DI. Okay, now since it's in data transfer instructions, I am putting a D out here. Okay, see the labels and how it is changing. So it becomes a D out here, right? And since there is no ALU operation here, I write an X out here and dash, and just neglect this R, which is okay, X and dash here. Okay, that means there is no ALU operation involved here, right? Similarly, and flag is also not required out here, right? So this is ST1 and ST2. I have just put two labels out here. Now what I have done is other contents from that memory which was being pointed out by Rx, I have got into DI. Now from DI I am getting it to T2. Again I am placing the contents of RY, okay, into the address output buffer. Okay. Now in DI register, now the second data which is from the memory which was being pointed out by RY, that is being brought to the DI out here. Okay, so this becomes now the second data is available in DI. The first data which was available earlier in DI, that we have moved to T2 out here, right? Now I am going to compare these two, so I will do a subtract operation. Okay, so T2 I am getting it to ALU, and DI I am also going to get it into ALU, and I am doing a subtract operation, right? If I am doing a subtract operation, and also I am putting dash, so this S has come, okay, in all these cases this is X dash N, so this N has to be here. Okay, this N has to be here, this S has to be here. Okay, so this S means, okay, what does it mean? I am putting S out here. Okay, that means the flag needs to be, because I am subtracting these two datas. Okay, the earlier data which I got, I have placed in T2. The next data from memory, it is available in DI. I am doing an subtract operation. So I am actually doing RY minus RX out here. Okay, so I told it will always do B minus A. So it will RY minus RX. So I am also activating the flag out here. Okay, that is why I have written S out here. Now there is a branch operation. Okay, out here. Okay, once it subtract here. Okay, whether it is negative or it is positive. So these are the two conditions which I need to check out here. So in between, what I am doing here, while these actions is being done, I am also increasing the count of the PC. So I am getting a PC value to the ALU and to the address out bus bar, so that the next instruction is being fetched. Because while I am doing this, the instruction can be fetched and parallelly actions can happen, right? So that's why I have inserted this PC increment in between. So I have IR out here. So this is instruction read operation. So here this is data read operations. I have put D here. Data read operations I have put D here. Here external data bus is not being SS, so I have put N out here. This is an instruction read operation. So that is why I have put an IR out here. So okay. So if you see here, EDB. Okay, so now the PC value of the program counter is put into ALU and address out bar. Since it is put into address out bus bar, so the data from the external test from the memory would come to EDB and it will be stored into the IRF. Okay, instruction fetch register. And also I am increasing the value of the PC by giving +1 to the ALU. So now the result PC +1 will be available in the ALU, and in the next cycle, you see from T1 it is coming to PC. Okay, whether it is N is equal to 0 or N is equal to 1 doesn't matter. So so the program counter will be increased. Okay, now if N is equal to 0, okay, it indicates that R is small, right? Rx is small, so I don't have to do any action right here. If N is equal to 1, right, that means Ry is small. Okay, so I need to now swap the data, because I have done subtraction of an Ry minus Rx, right, and if it is not negative, that means Ry is greater. Now right, I am doing Ry minus Rx, and N is equal to 0 means N is equal to 1 means it is a negative number, right? So I am doing that means Ry is small. Now I need to swap these data. So what I am doing is from Ry, the data of R by, okay, through B, through Ry is what? It is only indicating the memory location. So I am putting it into A0, okay, address. And what was the contents available of Rx? that we had stored in T2. So that data is available in T2, that we are going to put into D0. So the contents of Rx, initially Rx, now was stored in T2, now that will be written into the memory given memory location pointed out by Ry. So you see now into the memory location which is specified by Ry, you have the earlier contents of Rx being returned here. So the data gets swapped. One data gets swapped here. Okay. Now you have to do for the other data also. So you have, this is a data write in section. So you have dw. So this is x minus out here. This is n out here, right? X minus n. Okay, this is single block here. So this has come. X means we are not ALU is not being used here, and the flags is also not required here. Okay, so that is why it is shown like. And in the next what we have to do, we also have to update the other memory location. So what about that data which was available in RY memory corresponding to the RY register, that was available in DI register, right? So from a DI you are getting it into a T2 register out here, right? And then here if you see here, Rx data is being placed into AO, and from T2 you are getting it into DO out. So now here the swapping action is completed with this particular action. So this is again a data write out here. Okay. Here since again ALU is not involved out here, it is x dash n. This is also x dash n. Okay. Just this A is NA. Okay. NA and x dash n. Okay. So this has got shifted here. So this is x dash n out here. Okay. So before loading this PDF, I'll do these small corrections and do it. Okay. So this is x dash n out here, right? So this is how a sort operation is done. I think what we will stop it here, and